Good morning and welcome to my YouTube channel. My name is Dennis. Today I'm going to talk a little bit about the work that I've been doing with flow capacitors. Flow capacitors are kind of an offshoot or you might say a subset of supercaps. Both flow capacitors and supercaps are quite similar. At least in terms of the ones that I'm working with here. What I'm holding in my hand is kind of my baseline recipe for a supercap. If you take a look at my previous video, I start out with showing you how I make some of the carbon fiber cloth current collectors. But now I've progressed a little bit from developing kind of this baseline static supercap, and today we're going to talk about how it's migrated into a flow capacitor. Little background on flow capacitors, and I guess I'll mention at the end of this video I'll post up a list of several good references so you can become a little more familiar with flow capacitors. There's a number of papers and a really good patent published by the work that was being done at Drexel University. Okay, so flow capacitors versus regular capacitors. Lots of similarities. We've got, in both cases, a current collector. In both cases we have a separator, and the electrodes, at least the ones that I'm using, are a carbon paste spread on top of the carbon fiber cloth current collector. Stick our paper towel separator on that, complete the sandwich with a symmetrical half on the other side. And this little sandwich, when wetted down with our electrolyte, which in this case I've sort of settled in for now on a 5 molar potassium hydroxide, forms a nice little supercap. Performance of this baseline cell, I guess, isn't really great, but it's about 27 square centimeters in area. I don't know what the exact thickness of the material is, but when I take this sandwich, soak it up in the KOH, charge it to 1.3 volts, just a little bit above the limit for an aqueous electrolyte, discharge it through a 25 ohm resistance, I'll get performance that lasts somewhere in the 8 to 9 minute range. Obviously, if you could charge it up to twice that voltage using some of the non-aqueous, deep eutectic, or ionic liquid electrolytes, you'd get 4 to 1 improvement, and I'm sure there are much better carbons out there than what I'm using. If you're into, some of the graphenes or nanotubes or spherical carbons. But here we've got, for a carbon, a simple coffee ground up fish tank activated carbon. I mix that in a 4 to 1 ratio with some carbon black to increase the conductivity a little bit. And whether that's the paste in this static supercap, or as you'll see, the flowable liquid in my supercap, that's my baseline recipe. What I want to show you is how I've taken this standard cell and now progressed to the flow capacitor. I started to talk about some of the similarities, and now a little bit about some of the differences. Here, the amount of energy that's stored is related to the properties of the carbon. It's related to the size of this cell, the 27 square centimeters of area and its thickness. And if I want to store more energy, I can make more of these, stack them up, roll them, whatever. But I'm pretty much limited in terms of what the cell can do. With a flow capacitor, for a given size of electrodes, if you will, the amount of power that you can generate from your system is not limited by the energy produced by the cell, because the electrode in this case is infinite, or at least limited by external factors to the cell. The electrode is a liquid. In this case, it's, I guess you could call it a thick carbon ink, but it's not just a carbon ink, if you will. It's mixed with the electrolyte. So combining the electrolyte with the electrode, flowing that through the cell, storing it in its charged or discharged state externally, limits the total amount of power the cell can generate or store, if you will, depending on the size of that external storage. So you've disassociated the energy of the cell from the power of the cell. And that's kind of goal of the experiments that where I'm at today. Okay, so how do we do that? Well, I've come up with a little bit of a fixture here, if you will. This is one of the earlier versions where we have on both the anode and the cathode side, we have an inlet port to flow the electrode in, and we have an outlet port. That electrode flows over internally on each side of the symmetrical cell between the paper separator and the current collector. So we have a little liquid sandwich. We have the separator, we have the liquid that flows in, and we have the current collector on each side. So here on the anode side, input output, and then on the cathode side, the same thing. So far, this arrangement works very well as a static cell, meaning that the performance of that capacitor is about identical, if you will, of this, mainly because the electrodes in there, once they're coated with the liquid, are pretty much the same size performance limitations of this cell. So the next phase is now to get this electrode to be able to flow through the cell, collect the charged suspension, flow it back through the cell, etc., rather than charge and discharge in a static fashion. So to do that, we've been experimenting with various form factors. The latest form factor I'm going to show you here today, that'll be part of the next set of experiments, takes a base plate. This is a PLA printed base plate that I've designed. Here you can see the current collector, identical to what I mentioned in the previous videos. This is laminated inside of this cavity in this base plate with a little bit of epoxy on the back. We did experiment with various types of double-sided tape. It was sort of a little bit hard to control the thickness, although maybe a little bit messier. A thin film of epoxy on the back of this, and 5 minutes later you've got a nice current collector laminated into this base plate. Here are the input and the output ports, a couple of nylon fittings just finger threaded into the holes in the PLA 3D printed base plate. We've added a couple of other features here. Here you can see a little locating slot that helps the sandwich go together. So we take one side here, we put on our paper separator sandwich, close everything up, clamp it together I'll take some silicone, seal it around the edges, and I have a nice, quote, watertight cell that I can use for my flow capacitor experiments. That's where we ended up with this earlier design that worked fine as a static cell but had very poor flow performance. And what I found, not unlike it's been outlined in some of the research that's been done, is there's a fine line between the performance of the cell in terms of the many factors, mainly the gap that is formed between, in this case, the current collector and my paper towel separator. If I stretch that across this cavity, in my earlier cell, there was about 20 thousandths of an inch, about half a millimeter of gap. And I figured, okay, the nice thin gap means that the ions don't have to travel very far, and that should promote efficient performance. And I guess it did, except that as I wet the cell, the wet towel soaks into the current collector. Basically the gap becomes close to zero and you get no flow. Well, let's just increase that gap, let's double it. Well, now the ions have to flow twice as far. There is twice as much material, but again, these are carbon particles that, unlike this earlier cell, are compressed and sandwiched together. Okay, here they're floating, suspended in this KOH electrolyte. Depending on the concentration of the suspension, less to lower the viscosity to make it more flowable, but also less concentration means the particles are further apart, harder to receive the charge, and the overall capacitance is decreased. So we're playing with the trade-off between viscosity, concentration of solids, conductivity of the carbons, and the next step in my test then is to go with about a 1 millimeter gap. Unfortunately, the same sponge-like paper towel, and I say sponge-like because as this thing gets wetted, it soaks the liquid portion of the electrode out, leaving the solids portion. Now the solids viscosity is higher and it doesn't flow. So if anyone wants to suggest, or even better, donate a nice little polymer ion exchange membrane, that would probably help considerably with the performance. But in the meantime, I've come up with this little spacer, if you will, these little dots held together. They get placed in here. Here's one that this one's been tacked in place with some epoxy at the corners. So now we've got our little 40 thousandths, 1 millimeter spacer network here that hopefully will prevent the membrane from sagging and basically choking off the flow from the inlet to the outlet port. Or if this is the inlet and now the material is charged and stored in a container at the outlet port, then it's merely a matter of, like in this particular design here, inlet, outlet, charged material stored, turn it upside down, and just let gravity reverse the process. Now the charged material is flowing in, and the current collectors are removing the charge, the electron flow, the ion flow, electron flow external to the cell, and now the discharged liquid electrode flows back into its own storage tank. So you need 4 storage tanks, one for inlet, one for outlet on both the anode and the cathode side. And typically they would both flow at the same time, flow together. Okay, so that's where we're at. We're about ready with this new design with a controlled amount of spacing. We'll build up our sandwich. We'll put all this together. We'll put it under test. I guess once I put this together, what's worked out quite well is just clamp this together. It sort of snaps together with those features built in the base plates. And then I coat the seam with a little bit of silicone caulk, let that cure up overnight. And so far, we've had a nice watertight cell for testing. We're going to stick for now with the 5 molar KOH, about 18% solids for the carbon mix. The literature talks about somewhere in the range of 15 to 30% of solids. Higher solids, more capacitance, but again, the trade-off of viscosity and flow. So that's where we're at. Hopefully in the next few days or weeks here, we'll be able to test this cell, and we'll report back on YouTube the performance. If you have any other questions or comments, please let me know on the channel, and we'll hope to see you all here down the road. Thanks for watching.